All right, I'm going to go ahead and start. I will probably accidentally wander in front of the projector a few times. I'll try not to do that. And if the screen is about to hit me in the head, everyone gesticulate wildly. So as Rachel gave me a great introduction, my name's Emily McLinden. Can you hear me now? Okay. I'm a little nervous, just a little bit, so that will go away. So I'm going to tell you about a project I'm involved in at UT that's called HETDEX, and I'll explain what that weird acronym means. And then I have my little endorsement that HETDEX doesn't endorse astronomy on tap, but they should. So the tagline for HETDEX is 1 million galaxies, one giant telescope, one dark secret. So I'm going to walk you through what those million galaxies are and how we're going to find them, tell you about the telescope, the giant telescope we're going to use to find them, and the dark secret that we're trying to uncover with this project, which is the secret of dark energy. Do you have the clicker? No. So, without further ado. All right, so what is HETDEX? HETDEX is the acronym for the Hubble Telescope Dark Energy Experiment. That's a mouthful, hence the snappy little acronym HETDEX. The Hubble Telescope is 450 miles west of Easy Tiger in the Davis Mountains at McDonald Observatory, and that's what I have pictured here. Can I get a show of hands of who's visited McDonald? Yes. All right, well, you can ask any of those people if you haven't been yet that you should do it. We get something like 150,000 visitors a year. It's worth the drive from Austin. You can, there's almost nightly star parties. You can stay overnight in the Astronomer's Lodge, get tours of the telescope, so go do it if you haven't. So this is the largest telescope at McDonald Observatory. It's the HET, or the Hubble Telescope. And this is what we'll be using to conduct our dark energy experiment. And the dark energy experiment is the DEX in HETDEX. So the goal of HETDEX is mainly a dark energy experiment. We're going to try to understand one of the major outstanding questions in modern physics, which is, what is this dark energy stuff that we think we need to explain why the universe is expanding, and not only expanding but accelerating in its expansion, but we don't really know what it is. So we call it dark because we don't know what it is, and we're not terribly creative as astronomers. We don't know what dark matter is, so we call that dark matter. We can't see it. We don't know what it is. We don't know what dark energy is either, even though it makes up the largest fraction of the mass energy balance in the universe. What we do know really well is that normal matter, and by normal matter I mean you and I, your beers, the tables you're sitting at, the sun, planets, galaxies, all that stuff we can see, that's normal matter. We have that down pretty well. But then we have these two things we don't understand. Dark matter, we know it's there because we see it flinging stars around at the outer reaches of galaxies. We can detect its presence in galaxy clusters. Don't really know what it is, call it dark. That's one of the other major outstanding questions in modern physics, but what HETDEX is going to focus on is dark energy. This is this force that we know has to exist because we see that the universe is expanding, and not only expanding, but it's expanding and accelerating faster now than it was in the past. And the only way for that to be the case is if there's some force that we don't understand, dark energy, that's driving it. So HETDEX is going to try to narrow down the possible explanations for what that could be. All right, so how do we do that? Well, we know way back in the past, at the bottom of this diagram, we have the Big Bang. We know after the Big Bang, the universe expanded. It's continued to expand today. When galaxies first formed, way down here at the bottom, they were closer together. The universe itself was smaller, space was smaller. They were clustered together more. As the universe expanded, those same galaxies get stretched further and further apart as the space itself expands. And that continues into a process that process continues until you get to today, where our galaxies are, on average, certain distances apart from each other. If we can trace how close galaxies were together, let's say 9 billion years ago, 10 billion years ago, 11 billion years ago, if we can study how close they were together and how fast they moved apart from one another, we can start to narrow down which theories of dark energy are the most realistic. Because each theory predicts a different behavior back in 9, 10, 11 billion years ago. So we'll take data on galaxies, we'll see how close they were together, how quickly they started to spread apart from each other, and we'll be able to say, yep, that theory is okay. And nope, that theory, we'll throw that one out. So we probably won't get the final answer on what dark energy is, but we'll narrow down the possibilities. Oops, wrong way. So another way to think about it is, you guys have seen images like this in the news. This is a beautiful image of about 17,000 galaxies in the extremely deep field from the Hubble telescope. But when you look at this, this is essentially a two-dimensional image. You can tell me where the galaxy is in the sky, but you can't tell me how far away from me that galaxy is just with a two-dimensional image. So what we want to do, what we want to do is take that image and map it into 3 dimensions. We want to know which of those galaxies in that image are, let's say, 5 billion light years away. Which of those galaxies in that same image are actually 5, 6, 7, 8 billion years away. Which of those galaxies, those really small dots in here, some of those are like 10, 11, 12 billion light years away. So we want to take your two-dimensional image, stretch it out into 3 dimensions, build up a map of where the galaxies are, and then we can look at this 5 billion year old map, we can look at this 9 billion year old map, and compare how the galaxies are clustered once you have a 3D map. So how will HETDEX do that? How do you go from this big telescope in West Texas to actually making a 3D map of galaxies in the universe? Well, you do that not by making the pretty pictures you saw on the last slide. So nothing like that. What we're doing is we're going to capture spectra of galaxies. So you guys are all familiar with the concept of spectra. You hold a prism up to a light bulb or up to the sun, and it takes what looks like white light and it separates it into all the different components that are actually in that light. So it separates out different wavelengths of light. That's what we're going to do, but instead of putting a prism up to a light bulb, we're essentially going to put a prism up to each galaxy that we can detect and separate its light out into a spectrum. And then we can analyze those spectra, and those spectra will tell us how far away the galaxy is. So how do you know how far a galaxy is away when you look at its spectra? Well, we look for certain features in a spectrum. So these black lines represent various features in a spectrum. And you'll notice the pattern of those features repeat in each of the 3 spectra I've shown here. But the patterns seem to shift to the right as the galaxy gets very far away. So this is a nearby galaxy. You see these patterns. You look at a more distant galaxy, you see the same pattern, but they've shifted. You look at an even more distant galaxy, the pattern shifted more. So every time we take a spectrum of a galaxy, we're going to look for certain features like these, and that's going to let us say that that galaxy is 9 billion light years away, or 11 billion light years away, and separate out different galaxies and make a 3D map of a small portion of the universe. So then we get our 3D map. I'm back to 2 dimensions here, but bear with me. We get our 3D map, and we find those galaxies that were, let's say, 9 billion light years away. So I've drawn some blue lines that show you kind of on average how far away the galaxies are from one another, 9 billion, if the galaxy is 9 billion light years away. And then I'll add some red lines for the galaxies that are 11 billion light years away. They're farther away, they're a little closer together. So we take our 3D map, we do this sort of analysis to see how close together the galaxies are from one another, how long it took them to get from this close together, maybe 11 billion light years, to how quickly they got this far apart from one another. And that'll help us narrow down the possible explanations for dark energy. How do you do this? How do you go from having the 3rd largest telescope in the world, we've got that out in West Texas, what do you actually do with that telescope to get spectra? Well, you have to build an instrument that's never been built before. Nothing of this scale has ever been built before. We're building something, it's a massive instrument that's called Virus. And this massive instrument will be able to take spectra not of one galaxy at a time, but 36,000 spectra at a time. So every 20 minutes we'll be getting in 36,000 spectra. And some of those spectra will be the galaxies that we're looking for, that we're going to use to build up this map and to look for the evolution of dark energy. And it turns out we're not just going to look for any old galaxy. There's certain kinds of galaxies that are easier to find even though they're really far away, 9 billion light years away. So we're going to use a specific type of galaxy. Lucky for me, we're using Lymanalpha emitting galaxies. These just happen to be the kind of galaxies that I've spent my academic career so far studying. So I'm going to get a massive data set to play with. The dark energy is cool, but I'm really excited that I get a million galaxies to play with. So what's a Lymanalpha emitting galaxy? It's just a specific type of galaxy. Lymanalpha is a fancy name for an energetic transition in hydrogen. In far away young galaxies, you've got lots of protons and electrons floating around. They smack into each other and form a hydrogen atom. That hydrogen atom sometimes is excited. It has to de-excite at some point. When it does, we get UV light from that transition. And that's all that Lymanalpha is. It's UV light from excited hydrogen. But that also makes it an awesome tool for studying faraway galaxies. And it works like this. The galaxy is this little blob here. Let's say this is 11 billion light years away. When the hydrogen was excited, it got unexcited, it put out UV light. That light travels towards us across 9 billion light years or more of space. And because the space it's traveling in is stretching, the light itself also stretches. So what left the galaxy 9 billion years ago as a UV photon is no longer a UV photon by the time it gets to us. That's good because our atmosphere doesn't let UV photons in, or we'd all be fried to a crisp. That's what you wear your sunscreen for, is to cover up, the little bits of UV light that does get in. But because the universe has stretched this UV light into optical light by the time it reaches us, it can cut through our atmosphere and reach us at the HET in West Texas. So it's traveled 9 billion years to get to us so we can collect its light at the HET and use it to study dark energy. And it just so happens that Lymanalpha is a line. It's a bright light that we can see in lots of these distant galaxies. So it becomes an easy signpost to pick out galaxies. So a Lymanalpha emitting galaxy, it's just a galaxy with lots of UV light that we can detect. So we'll be collecting 36,000 spectra roughly every 20 minutes. About 106 of those spectra will be these Lymanalpha emitting galaxies that we'll be able to use for our dark energy analysis. And that comes out to about 6,000 of these galaxies per night. It'll take us about 140 nights over the course of 3 years to get to a sample of 1 million galaxies, and that's what we'll use to make our dark energy measurements. Just for perspective on how enormous these numbers are, my dissertation was 2 years ago. I had a sample of 33 Lymanalpha emitting galaxies, and that was a big sample. It took 5 years to compile. We'll get that 5 times over in the first 20 minutes that we actually start this experiment. If you're curious what a Lymanalpha emitting galaxy looks like, this is an image I've taken to detect Lymanalpha emitting galaxies with a 2.7 meter telescope in Arizona. So anything you can see here, these big white things, those are actually kind of nearby stars. Any of these little tiny smudges you can see, those are kind of nearby galaxies. If you want to see a 9 to 11 billion year old Lymanalpha emitting galaxy in this, you have to zoom in 5 times on that spot. And this little red circle shows you what a Lymanalpha emitting galaxy looks like. So it kind of looks like a blob. It's like 12 pixels. That's what Rachel and I spend our days staring at. But that's what a Lymanalpha emitting galaxy looks like to us, even though it's 9 billion light years away or more. But like I said, we're not actually taking images of these. We're taking spectra. So this is what a spectrum looks like. You have the different wavelengths of light. And when there's a lot of Lymanalpha emission, you get a feature that looks like this. This is just like those black lines in the earlier spectra I showed you. So we look for this feature, and we look for how that feature has moved, and that tells us how far away the galaxy is from us, and we can put it in our 3D map. So we're going to be able to do a lot of exciting things in the realm of constraining dark energy. But besides dark energy, those of us that study galaxies, Rachel and I, are going to be able to do lots of exciting studies about galaxy evolution using this sample of 1 million galaxies. You don't just use them for dark energy and then throw them out. Those of us that want to understand how galaxies evolved from 9, 10, 11 billion years ago to the present day, where we have galaxies like the Milky Way that we're currently residing in, those of us that study galaxy evolution are going to have an unprecedented data set to do that kind of analysis. And we're going to do it better than anyone else because we're going to have 1 million ancient galaxies. So that's where I'll leave it. Thanks, y'all, for listening. It's been awesome to see this many people excited about science here. You can follow me on Twitter, ask me questions there, and if you're more interested in HETDEX, HETDEX.org is where you want to head. Thanks.